This section is 9.3, multivariable linear systems. So really what this is about solving bigger systems than just the two equations, two variables types of problems that we had up to this point. Because if you have two equations, two variables, I would agree that the simplest methods for solving those are the substitution method or the elimination method. But the problem is that as you get to bigger systems, and what we're going to be looking at is three equations, three variables, but as you get to bigger and bigger systems, it is much harder to keep that information organized and to be able to do it in the quickest way possible. And so as we go through and do this, what I want you to keep in mind is that even though this system of three equations, three variables that we're going to be dealing with may seem like something that you could do in a different way, keep in mind that the idea here is that I'm showing you a method that can be applied to four equations, four variables, five equations, five variables, six equations, six variables, and so forth. So it is a way of organizing the work. And it still is incorporating a lot of the stuff that we've been doing up to this point. When it comes to just two linear systems with, a linear system of two equations, I should say. So two equations, two variables, but they're both to the first power. My favorite method probably is the elimination method. And this method that I'm going to be showing you does really incorporate the skills that you learn doing the elimination method. So a lot of these you can think about like that actually I am doing an elimination, but I'm doing it in a different organized way. Okay? So please keep that in mind as we do this. And so there's a certain way that we go about this. Also, the way that I'm showing you this is also something that leads into a whole nother method of dealing with things called matrices. And so there's a method to my madness whenever I'm showing you this stuff. It's not simply because it's like I want you to do it this way because it's the way I like doing it. It also lends to helping you with doing other things later on. Now, this year, because of COVID and all the different changes that we've had to make, we've had to limit how much we actually are teaching you in this school year. And so I've opted not to do chapter 10, which is the matrices. So you're not going to actually be able to see like how this does apply to matrices at the moment, but there's a chance that you're going to end up in future math classes where you might be doing matrices, and then this skill will help you with that. So we need to talk about a couple of things like what is row echelon form? So, and how is it, why do we want to put it in this form, and how is that helpful? Row echelon form is where you take a system of equations. So in this case, I've got three equations, three variables. So this one has x, y, and z. This one only has x and y. This one has x, y, and z. They're all to the first power, so they're all linear equations. We have three variables, even though this one technically has the z term missing. This is just standard form of my equations. Standard form is where you have x, then y, then z, and then the constant is on the other side. So all three of them are in standard form. And what I'm going to be showing you is how to take this and do some transformations. So this squiggly line that I'm doing here, that represents the process that I'm going to be teaching you. So that what you're going to end up with is a system that looks like this. So again, still standard form, but if we have x, y, and z in the first equation, notice the x is only has a coefficient of 1. I don't have it written there, but it have a coefficient of 1. The second equation, there's no x. And that's the way it's going to be every time something's in row echelon form. The first equation will have x, y, and z. It needs all three variables, and x needs to have a coefficient of 1. The second equation will only have y and z, and the coefficient of that y will be 1. And then the third equation will be missing x and y, and it'll only have z with a coefficient of 1, so 1z equals, and you have this value here. That's called row echelon form. So what I'm going to be teaching you is how to take a system like this and to do some manipulation, some certain operations that will change its form from looking like this to looking like this. Well, why would I want to do that? Well, once you have it in this form, you now know what z is. So I'm looking for an x, a y, and a z value. It's an ordered triple because we have three variables here. So instead of an ordered pair, it's called an ordered triple. And we now know what Z is. Z is 2. By the way, when you have an ordered pair or an ordered triple, or if you've got 4 numbers, it's always alphabetical order. So it's X, Y, Z. So if we had W as a variable here, then it would be W, X, Y, Z. But anyway, once you know what Z is, you can take Z, this value, and substitute it back in here. And get Y plus 6 equals 5, which would then allow you to solve for Y and get that Y is -1. And then you'd be able to take -1 and put that in for Y here, 2 in for Z, and figure out what X is. Well, that process is called back substitution. So it basically just means you are substituting back into the previous equation and getting what value is missing there. And then you're substituting those back into the first equation and finding the value that is missing there. And so that's what back substitution is. So since Z is 2, which is what I just did, I can substitute that in and find Y is -1, which is what I was just demonstrating. And then you can go back and you can put -1, the Y value in the first equation, 2, the Z value back in the first equation, and find X. And that will give you what X is. And then you can write your solution, which is an ordered triple where X is 1, Y is -1, and Z is 2. Now, I did have this note in here in case I forgot. It's called the step pattern. So it's a stair-step pattern. So yes, the first equation has to have all 3 variables. The second one only has Y and Z. And then the third one only has Z. And then the leading coefficient should be 1. So 1x, 1y, 1z to put something into this form. So how do I do that? How do you transform it, a system into row echelon form? Well, the method is called Gaussian elimination. Okay, there's a famous mathematician named Gauss, and they named this after him. But there's a process to it, and it's like anything else. It's like if you go to school, there are rules. If you play a game, if you play a sport like soccer or softball or football, or if you're playing Monopoly, there are rules to the game, and you can only do things within those rules. Well, transforming things into row echelon form has a set of rules, and as long as you can learn how to use those rules, you can figure out how to manipulate it and transform it into what that row echelon form look like. And so here are my rules. Operations. So first of all, I can interchange any 2 equations. So we had that original problem, and I had 3 different equations there. And anytime I wanted to, I could say, you know what? I want this third equation to be the first equation. Why? Well, maybe it has a coefficient of a 1 in front of the x, and maybe the other equation doesn't. So by simply switching the order of my equations, I can maybe get that in the place that I want it to be in. So there are times when you might go, hey, wait, I want this equation to be this one. You can do that anytime, but you have to switch the entire equation with another equation. You can't just take part of it. So that does come up. The second one is you can multiply any equation by a non-zero constant. Now I know it says multiply, but that really means you could also divide, because if you wanted to divide by 2, it'd be the same thing as multiplying by 1/2. So the only thing you can't multiply by or divide by is 0. Because if you did that, it would eliminate the equation altogether. We need that equation in there. So if anytime you want, you can take an equation, let's say that all of the coefficients are multiples of 2. And I really would like to have like one of the equations be a 1. Well, I could divide them all by 2. And it's still, because you're doing it to the entire equation, that's allowed to be done. That is the equation property, the addition property of equality for equations, sorry. And so that is something you're allowed to do. So that does come up sometimes. The most common one, though, is rule number 3. So why they made it rule number 3, I don't know. But this is essentially what the elimination method is. This says you can add a multiple of one equation to another equation and replace either equation. So that sounds really confusing. But really what it is it's saying you can take any 2 equations you want. And you basically kind of like pull them aside for a moment and manipulate those two. Take those two equations and you can do the elimination method with them. So you can use those two equations together to eliminate either x or y or z, whatever it is you want to eliminate. Typically it's x or y because all three equations are supposed to have a z in them when they're in row echelon form. So we don't want to eliminate the z, but typically it's like to eliminate the x. So you kind of pull them off the side, you eliminate the x in that system of those two equations that you pull out the side. Then you take that answer and you replace one of those two equations you started with. So let's say you took your second and third equation together and you eliminated x by combining them together. Well, then you'd go back, you still have to keep one of the equations you started with. But one of those two equations you can get rid of and replace it with the new equation that you came up with. So this is really the elimination method. So as I was saying before, it's not like we're coming up with something completely new. The elimination method is still something we're using. It's just kind of hidden in this problem, or these problems. So I'm going to demonstrate how to transform this into row echelon form. And what I've attempted to do is I've tried to come up with a way to use all of those different rules. Okay, so it helps if you know where you're going with this. So keep in mind, my final goal is to have this system of equations where I have 1x and then something y, something z equals something. That's what my first equation needs to look like. My second equation needs to be 1y and then something z equals something. So basically, there should not be an x term there. And in the third equation, there should not be an x term and not be a y term. All there should be in my third equation is a 1z equals something. So I don't know what this number is going to be. Right now, those numbers are 3, 6, and 0, which, by the way, I think that if you are using the notes that I provided for you, that there is a 17 right here instead of a 0. You need to change that to a 0. That was just me using it from a previous problem, and I left the 17 from the previous one and didn't fix it. So this is what I want it to look like. So there's a process to this. Essentially what I do is I focus on getting this 1x. That's the first step, is I try to get this 1x into place. My second step is I will then try to get both of these to eliminate this x and eliminate this x. So that's going to be the elimination method that's going to cause that to happen. So I can do that in any order, but that's my second step. Okay? Now, my third step can either be getting this 1y, this to be a 1y, or getting this to be a 0y. It doesn't really matter. But so it's kind of like these two are tied for the third thing I'm going to do. Don't know why it won't let me write that down there. But this is the third thing I'm going to do. I'm either going to get the 1y and then get the 0y, or I'm going to eliminate this y and then turn that into a 1y. It really doesn't matter which way I do it. But this is the process that I'm going to go through. Get the 1x, eliminate these, get this 1y and the 0 in place. It doesn't really matter which order I do that in. Okay? So that's my goal here. And I realize my screen changed on me, but that's my goal. Let's see if I can back this up. Okay, there we go. So back to that previous problem. So how am I going to do that? Well, again, I've got three options. And one of my options is to take any two equations and switch them. And I see that this has a 1x. And I want to have a 1x there. So I'm just going to take this row, and I'm just going to swap those two rows. So somehow you need to be making notes to show me like what you're doing each step of the way. So I'm just going to rewrite my equation, my system of equations, and I'm going to put the 1x plus y plus z here on top equals 6. And then my second equation is going to be the 2x minus y plus z equals 3. And my third equation is going to be this 3x minus z equals 0. And I know that some people are going to be like, oh no, that's missing a y there. That's good. I wanted to have that be gone. But what you need to focus on is just doing these things in this order. Don't look ahead at what's going to be in the problem, because by the time I get there, that probably won't be a 0, and I'll have to turn it into a 0y. Okay, because my first focus is getting this 1x in place. I did that. My second is to get these to be zeros. So I am going to be taking this system. I'm going to leave the first equation alone. But I want to change each of these other 2 rows. So I want to manipulate this row and get rid of that 2x. So think of this like the elimination method. I don't want to worry about this bottom equation. I'm going to use these 2 equations. That's a 2x. If I want to eliminate that 2x, I would need this to be a negative 2x. Then I could add them together and eliminate that. So here's what I'm going to do. I'm going to make a note of that. So I always take the one that has the 1x. I'm going to multiply the top row by negative 2. And then I'm going to add it to that one. Now I'm going to do my work off to the side. Because once you get good at this, you can actually just write this down and then do this in your head and write down the answer here. But I'm guessing that many of you are going to be like, well, this is confusing. I don't want to be doing that in my head. And right now, I don't want you doing it in your head either. So I'm taking this top row. I'm doing this like scratch work on a piece of scratch paper. I'm going to take that top row and multiply it by negative 2. So negative 2x minus 2y minus 2z equals 6. Now, just because I multiplied it by negative 2, notice I recopied it over here. I'm not changing that equation. I'm just using it temporarily. I'm taking this row or this equation, and I'm temporarily multiplying it by negative 2. And I'm taking the second row, which is 2x minus y plus z equals 3, and I'm going to add those together. These eliminate, and I get negative 3y minus z equals 9. So see this new equation I get here? This is where that rule number 3 said you could combine 2 equations together and then replace one of them. I can't replace the top one. I don't want to replace the top one. But I'm going to replace this one with this new equation. So I'm going to put the negative 3y minus z equals 9 right there. Now I want to do the same process to this third equation, because I just eliminated that x. I need to eliminate this x. I need to eliminate this 3x. So I'm going to do the same thing. So I am going to take this top equation again, and I want to eliminate that 3x. Well, if you're using a 1x and a 3x to eliminate that 3x, you need that to be a negative 3. So I'm going to multiply by negative 3 on this top row. Again, I'm not changing it. I'm just going to multiply it by that temporarily. So I'm going to multiply the top row by negative 3. So negative 3x minus 3y minus 3z equals negative 18. I feel like I did something wrong in the previous problem. When I multiplied this by negative 2, that eliminated it. Negative 2 gave me that. Negative 2. I feel like that should have been a negative 12 plus 3, so that should have been a negative 9 there. I think. We'll find out here in a moment, but I'm pretty sure that that's what I should have done. I could actually back this up because I erased that. So negative 2, negative 2, negative 2, that should have been a negative 12. And when I added, that would come out to be a negative 9, and that's why that is a negative 9 right there. Okay. So if you're watching this, I apologize. You're probably going to be like, oh my gosh, why'd you do that? Hopefully that cleared up that problem. So I am taking this top equation times negative 3 and adding it to this one. So the top equation becomes negative 3x minus 3y minus 3z equals negative 18. So you can see that mistake is definitely demonstrating to you something that you've got to be very careful of. I had to multiply everything by negative 3. And then I've got 3x and I've got minus z equals 0. So when I add these together, I end up with a negative 3y minus 4z equals negative 18. and I'm replacing this equation because I'm not interested in replacing the top one. It's the way I want it. But this one becomes a negative 3y minus 4z equals negative 18. So I have completed my second step, and I've got these to be zeros. Now my next step is to either turn this into a 1 or turn this into a 0. Well, to get the 0, all you basically do, anytime you're getting a 0 in a spot, you're doing the elimination method. So I think that's what I would do next, is I would go ahead and get that 0 into its spot. So what that means is that I'm leaving the top equation alone. Notice, since I moved it, I haven't had to do anything to that other than use it to eliminate some stuff. And so then I have this negative 3y minus z equals negative 9, but I'm going to get a new equation here because I want to eliminate this y. So again, how do you eliminate that? Well, one of these needs to become the opposite. So I would take maybe this equation and multiply it by negative 1, and it would become 3y plus z equals 9, and I would add these together and get negative 3z equals negative 9. So that would be my new third equation. Now I can go through and again this and this. So that's actually the fourth. I'm not sure why it won't let me write down there, but this is the fourth step, is to always get that 1z at the end. Well, I can turn this into a 1 by simply dividing this whole thing by negative 3. And I can do the same thing on this one, divide by negative 3. I need a little bit of room here. But as I do that, my top equation is still x plus y plus z equals 6. This equation now becomes 1y, which it's supposed to be, plus 1/3 z equals negative 9 divided by negative 3 is a positive 3. And then this equation becomes just 1z equals 3. This is row echelon form. Now that I have it in row echelon form, which is what I was supposed to do, that's the first step. So that's my first answer. That's row echelon form. Then it says it wants me to use back substitution to find the solution here. So if I do that, I substitute in 3, I would get y plus 1/3 times 3 equals 3. So y plus 1 equals 3. So y equals 2. And then if I go back to the first equation and I put x plus 2 plus 3 equals 6, I get x equals 1. So my ordered triple would be 1, 2, 3. And my board has just gone crazy. And it's moving. I guess I accidentally hit the board there a couple of times. And it went back to here. So now you can see that is the solution that I should have had. If you go back and you plug it into the original equation, 1, 2, 3, and for x, y, and z, it will make all 3 of these true.